Kagglers. I am here today with David Ha from Google Research, and you're a research scientist, right? Is your job title?
Yeah, I am. Yeah, I think so.
That's what they tell you on the paperwork. And I reached out to you because we actually finished today, the day we're filming this, not the day this comes out, your paper with Adam Geyer?
Adam Geyer, yeah.
Geyer. Oh wow, I've been very off. Just gonna write that down really quick.
He was our first intern in the Google Brain team in Tokyo.
Oh, cool. And he's now a faculty somewhere.
So he's a PhD student. So he's based out of Europe at the moment, and Adam also works for this. He's doing his PhD partially under this institute called INRIA. So they're a pretty big research institution in Europe, and his focus is on evolutionary computation. Mm-hmm. So like artificial evolution and looking at like novelty search, like as opposed to more of the machine learning, like here's a neural network architecture, let's find a way to train the architecture, or here's a data sets, like the typical Kaggle problem is like, here's a data sets, let's find some model to model the probability distribution really well of this data set. Where he's coming from is like, less, I guess the evolutionary computation community is more like it's less mainstream. They're more like, okay, let's take a look at the forest for inspiration. Let's see how biological organisms come to be, how life became what it is now, and what, like, as opposed to let's get a high accuracy on a particular benchmark. So I was kind of surprised how, apparently I saw on Twitter that our paper was selected as a reading material for Kaggle. It's kind of surprising to me because like it's not a nice research work at its current stage. It's not that useful for a Kaggle type of contest, but maybe with some work in the future, it could branch in that direction.
Yeah, and I would say one thing that I've learned is to never underestimate the Kaggle community. Like if there's something new and interesting, they'll immediately start like playing around with it and applying it and trying out different things with it. Yeah. So speaking of how useful it is, I think the biggest questions I had around the method, and just as a quick review for people who haven't read the paper or seen the thing. Oh, also congrats on getting accepted to NeurIPS.
Yeah, thanks. Yeah, I mean, so this is like the paper actually. We did it on a bunch of reinforcement learning tasks, but we also, like, Adam also tested the method on MNIST classification, and it's like we got like the best accuracy we can get is 94%. So it's actually like much lower than the state of the art, which is like close to 100%. So I feel like it's probably one of the papers that got accepted at NeurIPS with
like the lowest accuracy
score. So that's something to be kind of like, maybe that's something to be proud of, like, how bad your result could be versus the state of the art, and yet still get into NeurIPS.
Yeah, but also a much smaller model. So comparing like model complexity as a factor, I think there's definitely something to be said for the approach. What was I saying? Sorry, it's a little bit late for me here. I think the main question I had about sort of the utility of this going forward, and of course, super early stage research. I get like you're just starting out, you're starting to explore this research program. I expect we'll see quite a bit more from Adam as well as he continues his work. I'm assuming his is. How does it compare to tuning neural networks with a fixed structure in terms of, I'm assuming the compute cost is a little bit lower because you're not doing any sort of weight updating, but my intuition here, and you can tell me if I'm right or not, is that it takes relatively as long because you have to do many, many, many generations to get to a point where you start to get good results, where you're changing the networks and adding things and seeing what works. Am I close?
Yeah. So like I think the motivation behind this research, like we're not claiming we got there, is to be able to come up with useful building blocks rather than the final solution to do some task. So kind of like we're actually motivated by examples in the deep learning literature. Like for instance, there's a line of work on looking at how convolutional neural networks, the conv operation actually is a very useful prior to do any image, image recognition or image understanding task. So there's a line of work actually that looked at, okay, here's like a deep convolutional network, like a VGG or ResNet architecture. They actually studied how effective it is because these networks still are useful even when the weights are randomized. So like there's been a work, it's referenced in the paper, but a few years ago, someone took a deep convnet and randomized the weights, and they showed that this network can still be used for style transfer. So which is a useful task. There's another paper called a deep image prior from a Russian institution 2 years, I think 1 or 2 years ago, and they showed that randomly initialized deep convnets can be used for things like image inpainting. Like if you take off a block of image, you can still guess what it is without any training at all. So there's that line of work. There's another line of work on recurrent neural networks, like from Jürgen Schmidhuber, where they showed that like a very specific type of recurrent neural network, like LSTM, for instance, is much more effective at predicting time series with random weights or like evolved weights compared to using the same architecture but with a vanilla RNN, like just a normal, the most simplest RNN. So there's something to be said about an architecture that still works when the weights are random. So our hypothesis is, okay, maybe that's a useful method to come up with new building blocks. So if it has been shown that certain building blocks work when the weights are random, why don't we start by having random weights and evolving architectures from scratch that will still work with such random weights? So that's where we're coming from. We're trying to initially look at the problem of finding useful building blocks. It's like we already have convnets, self-attention layers, LSTMs, and these can be combined in various ways using human engineering or even using neural architecture search to be combined into like the ultimate architecture for a particular task. But what we want to do is, can we actually find these building blocks rather than finding ways to connect them? And we're not there yet, but I think this work is a step towards that. And the intuition is having architectures that will work when the weights are random, or at least when the weights, we discover pure random weights is so hard to get it working. Adam discovered that we actually need to share other ways to lower the minimum description length, for it to get it to working. And perhaps this is a way to find more useful building blocks. So this is one inspiration. But of course, there's also a link to the biological the literature, and especially like this paper actually picked up quite a bit by the neuroscience community, especially a lot of the recent work, recent position papers written about how animals learn, and there's a certain innate structures in animals where, like, dolphins can swim the first day, the horses can walk within hours, and so on. So perhaps there's also an amount of innateness in the structures, so that the agents can already sort of perform a task on day zero as a zero shot, and from there maybe it'll be easier to fine tune the weights that way. So that's another motivation. It was not really set up so that, okay, let's try to find a method to do this task really well. It's more of like a general way of thinking. For future work, we think it might be useful for like to kind of discover networks that are useful inside of particular environments where there's many different types of tasks. And if we have such inductive biases for these networks, perhaps we can show some generalization properties on a new task. So like for instance, if we're trying to evolve an agent or train an agent inside a virtual environment in someone's backyard, like a simulation backyard, and that agent has to learn to play with the toys in the backyard with no clearly defined goals. Perhaps finding the very best, like a weight agnostic architecture that is suitable for playing, that architecture might be useful for actual task that is not playing, but for task that requires things inside the backyard, like like shoveling this toy over there, or bringing like hiding this inside the sand or something. So that's kind of the intuition, like how do we eventually get to the state where we don't need to train the agents every time. It has some sort of an innate structure so that it's easy for it to learn things within an environment. So yeah, perhaps this could be useful for the Kaggle community in the future. But honestly, I haven't realistically haven't thought of I don't spend my time like sleeping on how to make weight agnostic neural networks get the #1 grandmaster level on image segmentation.
Yeah, I don't expect you to. I think there are people who have that one covered for sure. Yeah, but it almost sounds like, I mean, again, this is very early stage research. You're envisioning a point at which we have sort of a set library and we're like, oh yeah, this is the network structure that works really well for like picking objects up. This is the network structure that works really well for, I don't know, moving in fog where you can't see very far, things like that. So there's specific behaviors, and you're thinking more agent-based, but I guess you could extend this to things like vision or maybe NLP, I don't know. My prior as a linguist is that language is a much more complex behavior than pretty much anything that we do physically in the world to interact with objects, and I'm sure there are people who would disagree with me on that one, but yeah, I would be interested to see how well this would work on a language problem.
Yeah, that would be it. That's a very interesting problem to think about. I actually think the language NLP is one of the most challenging areas of research. Like there's a lot of work recently on training large models as a language model, like all this, like, as you know, BERTs, XLNets, and this whole line of work, and using these features to get state-of-the-art results on a variety of NLP tasks. But there's also some studies on. It's interesting to look at the failure modes of some of these models to get the limits. So of course we have very good statistical models on language, and that's very useful. Maybe like humans probably have the equivalent of that. But it's to me it's interesting to find out where the limitations are and how we can address that, or perhaps like coming from WANs, like where we can automatically try to find ways to address that. Like as you talked about, like as practitioners in machine learning or Kaggle participants, you're given a problem and it's based on our heuristics. Oh, this is a vision problem. Let's throw in some comments. Here's a language problem. Let's put in some self-attention. But what if you have a Kaggle competition where the sponsor or the task involved is a task such that we don't know what prior we should use? I can't think of such a task because usually it's either language or vision. But who knows? Like maybe, like the the cryptography or trying to find life in space, something that you actually is like something.
You don't know what success looks like.
Yeah, we don't know what the task looks like. Then in that point, like we can either treat our deep learning tools as a hammer and everything is a nail, or we can find this is this is not a nail, but maybe we can do an automated search of the hammer.
Yes, yeah, definitely. And maybe you find that the hammer is screwdriver shaped and is used like a screwdriver.
Right. Yeah. So perhaps perhaps one way is like if we have a novel problem, we can find like a toy version of that novel problem, and then find structures that have a strong inductive bias to solve a toy version of the real problem, and then see if we can scale up, like find these building blocks, and then try to scale it up afterwards for the actual problem at hand.
Yeah, definitely. I think that's an exciting area. I'm interested to see where it goes. I don't know. I know it's very, very early days for this research program, and I'm just like, what's gonna happen? I want to know. So do you have, I know we've talked quite a bit about this paper, which I'm very excited about, but is there anything else that you wanna share with the Kaggle community? Maybe a paper you've read recently that you're like, oh, that sounds cool. And it doesn't have to be something that you think would be immediately applicable to a Kaggle competition, just something interesting that you wanna share.
Let's see. I don't know. We kind of related to, not directly related to this paper, but because we were talking about training agents to do many tasks earlier, or the issue of generalization for RL agents. So there's a at the NeurIPS conference later on this year in Vancouver, there's like an official competition called the Animal AI Olympics.
Oh.
Yeah, that's I thought that was kind of cool. And it was what I described earlier. I briefly looked at the environment, and it's like they set up this like a 3D looking virtual backyard with a bunch of toys, and the agent is basically like an animal creature that has a low dimensional pixel input of the environment. And there's a set of training tasks. So the participants have to can use those training tasks as a guide to train their animal agents to do those tasks. But the contest is about evaluating the agents on the held out test task that we don't know about. The thing that's interesting is is still in the same environment. So like you're still kind of in the same backyard. So perhaps learning some behaviors that do well in that environment would allow the agents to do well on the test task as well. So I feel maybe like this sort of a contest, it's kind of a bridge between like the research that we did and something the Kaggle community might be interested in, because like there is like a leaderboard and a set goals and so on, and it also addresses the problem of one thing that I'm really interested in these days is like the domain transfer, like a domain adaptation, where your machine learning algorithm is evaluated on a set of tasks that is intentionally not in the same data distribution as the training distribution, and that this is like kind of like a simulation version of that problem. You have an animal, in a backyard training on a training task, and evaluating on unknown test tasks. But it could be like it's applicable to the real world as well, because I'm sure like in Kaggle competitions, the companies or the sponsor or the events specifies a training set, and you on your held out test set. Sometimes it comes from the same distribution as the training set, but like I'm not. Tell me if I'm wrong, but sometimes the test set is also comes from a different distribution.
That sounds possible.
I don't know. Like what are your thoughts on that as a Kaggle organizer? do you see that as an interesting, like for companies to actually use Kaggle to help them find, or organizations to actually tackle machine learning problems? How do they think about, okay, you have a data set, but of course in the real world, the data distribution is not going to be the same as the one you provide in a contest. Like how do they think about that?
Yeah, that's a good question. I should say I don't actually put together the competition, so this is just sort of like what I've heard from the people who do that, and not like my firsthand experience. I think the main value, sometimes the main value in a Kaggle competition is that the thing that you get out does the tasks that you do want to do, and you had like, you covered a lot of your possible distribution and the input. So I'm thinking here like the whale identification tasks, like, there's lots of different weather conditions and like angles and whatnot. Or I guess it's satellite, so some different angles. But sometimes the value of the competition is discovering a new approach that they hadn't thought of previously. So I'm thinking like the what was the real estate one? Zillow. Zillow's one, the thing that they were most looking for wasn't like necessarily a completely new way to calculate their score, but new ideas that they hadn't tried yet because they'd been working on it for quite a while with their team, and sort of seeing what works and having people try things out and coming up with new ideas. And I want to say somebody who did well in the Zillow competition got hired at Zillow, but it's late. I could be making that up. I'll check on that. I'll make sure that's the true statement.
No, interesting. I also heard from like a secondhand stories that usually the organization might not use the very best solution, but they might use like the second or third or even fourth place, because maybe it scales better, it's simpler, or maybe it generalizes better to another distribution. And I think as the generalization to unknown distributions, whether in machine learning or in RL or whatever, or in languages, NLP, I think that's gonna be an important and interesting topic in machine learning research.
Yeah, definitely. In the NLP space in particular, people are talking about zero-shot multilingual learning. So obviously doing things within the same language is much simpler than doing things across two languages or multiple languages. So yeah, it's very much an exciting and active area of research.
Yeah, it's like if I think about it, like the pipeline, the machine learning problem of here's a big data sets, here's a training set, and here's a validation and test set. If they all come from the same distribution, I think like a lot of these problems are almost solved, in the sense that people know how to do them. People almost solve, as in like people also understand the weaknesses of these deep learning approaches, but like it's kind of like a well-known methodology. Okay, you have a test set, your training set, your test set comes in the same distribution. Let's put it in a deep neural network, and let's do ensembles and then crank it up and do a bunch of hyperparameter tuning, and off you go. But I actually feel that in the research world, people are moving beyond this, and they're actually looking the problem of your test set is not known.
Yeah.
And that's gonna be that's what I'm interested in the context of RL, and even in a broader picture of generalization. And I think maybe like the Kaggle community will probably be interested in these type of research directions as well. Especially as perhaps in the future more Kaggle competitions might actually be testing the generalization ability of agents or algorithms outside. Maybe it's when these weight agnostic networks will shine. Who knows?
I can also see the sort of evolving library, because Kagglers will often, especially after a competition end, share their work. I could see if they do tend to, like, they start to do well as part of a very large ensemble, because that's how Kaggle works, having a library develop of like, oh, this is the structure we use for X tasks, and everyone starts to use that. So there could be like an emergent community use as well. Again, like, I'm excited to see where this goes. I think it's a really interesting and different way of just approaching deep learning problems. I don't know that you would call it deep learning.
Yeah, I don't know. I would call it deep learning either. It's just weird.
Yeah, I love weird research, and so do Kagglers apparently, because they voted for the paper. I don't know if you saw. There was a number of papers. I know EfficientNet was one of them, and then there was an NLP one, and they were like, no, we want that weight agnostic one.
I really like the EfficientNet paper as well. I think it was a very novel approach on how to like do architecture search in a confined source space. I think that's going to be very useful.
Maybe one day we'll read it in the reading club. Hopefully. All right. Well, I want to start wrapping up because I have to go to bed.
Yeah, thanks for staying late.
Is there any last thing you want to share or shout out, or I know I already asked you a similar thing.
No, I don't want to keep you here so late. So.
Thank you. Yeah. Thank you for making time for meeting with me. I know you're busy, and I think this was a really interesting conversation.
Me too. Thanks. Well, have a good day.
Yeah, and maybe I'll get a ticket to NeurIPS and I'll see you there. Maybe not.
Yeah.
We'll see.
Hopefully we can meet up there. Yeah.